All right, here is our first lesson of Chapter 1. You're going to see a theme in this chapter that the learning targets are pretty, there's 10 of them total. They're kind of lengthy. There's a lot of stuff in each one. So these lessons in Chapter 1 kind of feel like we have a variety of topics, all of which deal with kind of functions, graphing functions, and working with equations that represent functions. But each lesson kind of feels like we're just jumping around and doing a whole bunch of stuff, because we kind of are, because relative to what you've done in the past and what we're going to do this year in Precalc, a lot of the stuff in Chapter 1 isn't super difficult. So you'll see that we're covering a lot of topics. And you can, right underneath the label of the section, you can read through and, and take a look at, as to what those particular skills are. Great place to start is just the coordinate grid itself. Very brief summary. The Cartesian plane is its formal name. You may have referred to it as an XY grid, maybe a coordinate plane. I know the E is cut off there. It's not the coordinate plane. The coordinate plane. Whatever you call it, and I just want to make sure you're good on all the terminology for it. It is a system that we use to compare two variables to each other. At its core, that is what it's all about. We have a horizontal axis that we call X and a vertical axis that we call Y. Those are the names of the two variables, and sometimes we change the names depending on a problem. But that's kind of their typical, the typical names that we give them. The first coordinate is always the X, so I've got this first point that I'm now plotting. There's 0, 0. So now 3, 0 would tell me go 3 units to the right. Don't go up at all, so I'd be right on the X axis. 3, 4 takes me up here. And that is it's no longer on an axis, rather it's in a quadrant. And quadrant number 1 is where both the X and the Y variable are positive. Good time to just go around and label the others. If we were over in 2, you find there X coordinates are negative, Y coordinates are positive. Here's 3, where both are negative. And finally quadrant number 4, where the X coordinate is positive and your Y coordinate is negative. Now we've got 2 other points to plot here, -1, -2. Notice both coordinates are negative, and that takes us down into quadrant 3. And then -2, -3, same deal. That one is also down in quadrant number 3. All right, we have a method on a coordinate grid for determining how far apart 2 points are. Okay, now keep in mind with the distance formula, the coordinate plane is really versatile. It can represent a very wide variety of situations. It could be like a coordinate grid on a map, for example. A situation where finding the distance between the 2 points would be a pretty relevant thing to do. The distance formula is as follows. We say D is the square root of x2 minus x1 squared plus y2 minus y1 squared. Now I've already got 2 points. You probably noticed that the coordinate point 3, 4 and the point -2, -1. I want to figure out the distance between those 2 points. Just to illustrate on our graph here. The length of that line segment that connects those 2 points is what I'm after. Okay? And every time we touch on the distance formula, I always like to give ourselves a reminder that it really is just an application of the Pythagorean theorem. Okay? Which you've seen many times. First time you saw it in geometry. Okay? And you can see if I draw in those sides like that, all of a sudden we have what looks to be a little right triangle. Now if I just count the grids on each side, I can see that this triangle that's formed, one side is 5 and the other side is 3. Okay? Now you'll see a really particular relationship of how we got that number 5. If we took, and this is now referring right up to here, the difference between the two x coordinates, well, that would be 3 minus -2, and notice that would be 5. You'd probably think of it as 3 plus 2, which is 5. Okay? One thing I need to adjust here, you probably caught it already. That's +1. Hopefully, hopefully this is one of those examples where as soon as you saw it, you're like, wait a minute. You've got a coordinate point there, but that's not -2, -1. That's -2, +1. If you were concerned about that, you were correct. And now this 3, we have 2 positive numbers here, so it's a little bit easier to see the relationship that if we take 4 minus 1, that's where we get that 3. And notice that side length is really related to those y coordinates. Okay, so now if I didn't want to do this on a graph every time, I wouldn't have to. That's kind of what the distance formula is all about. Is we could have just used the coordinate points, and if I was just given the points and didn't have a picture, I could still do this, because I could take 3 minus -2 plus 4 minus 1. And you got to be careful at that step, because that's the downside of formulas. The nice part about them is they generalize a pattern, so if we recognize that pattern, we can make a calculation very efficiently. That's what formulas do for us. The downside is if you put one number in the wrong place, you're not going to get the answer that you were looking for. I've got everything where it goes. So this becomes 5 squared plus 3 squared. That would be 25 plus 9, which would be the square root of 34. That can't be simplified, and so that would be what we would refer to as our exact answer, because the square root of 34 is a very long decimal. Goes on forever. Never ends, and no pattern. That decimal wouldn't give us any pattern that would repeat. Now that's nice that it's exact, but it's has some downsides that it's a little harder to visualize how big that quantity is. If you went with the approximate answer, it's easier, of 5.83. Now you could, if you thought about the square root of 34, you could get to the point where you're like, yeah, it's between 25 and 36. Okay, it's going to be somewhere between 5 and 6, quite a bit closer to 6. Well, okay, that's probably going to get you to something like 3.7 or, 5.7 or 5.8. Okay? Another little formula we also use on the coordinate plane quite a bit is the midpoint formula. Okay? It kind of looks like the distance formula because it's in terms of x1 and x2, but it does something, fundamentally different. Okay, we're not trying to find the distance between these 2 points, and I've got 2 points here again. Maybe let's double check now that I labeled them correctly. 9, 3, -5, -3 looks pretty good. With the midpoint, we essentially just take the average of the x's and then we take the average of the y's. Okay. Notice this formula doesn't give you a number answer like the distance formula did. Distance can be expressed with a number. It just takes one, right? How far apart are we? Well, we're 10 miles apart. Okay. Not really, but just a hypothetical example. It just takes one number, 10. We're looking for a location and on a coordinate plane that's comparing two variables like the one we so often use. It takes two numbers to describe that location. And this formula gives you two numbers. So I take my x's, -5 plus 9 over 2, 3 plus -3 over 2. That would be 4 over 2, which would be 2, and this would be 0. So that would be this point right there. I can kind of test it on my graph here. Does it look about halfway in between? And I think it does. I think it does. I'm pretty convinced here we did this correctly, and we've got the point that's halfway in between. All right, a couple examples with some context here. All I want you to see on these is that it's important to just read the problem thoroughly and make sure you're clear which of these two, right? Is this point, or is this problem, is this leading us towards finding a point or a distance? Okay, what it wants is the length of the pass. And it's got like a coordinate grid kind of laying over a football field where the distance across the field is x and the distance down the field is y. So these two formulas that we've just seen, I'm going with the distance formula where I'd take the difference of the x's, which would be 40 and 20, and then the difference of the y's, which would be 28 minus 5. Okay, notice the work that you're going to see here. This is no different than the one we did before, right? The new element to this problem is it's got the context of football, okay? But the work that we have with it is going to be just like the other one we did, even though that problem had no context, right? Where the context, the element it adds is we just have to read the problem thoroughly and be sure we know what to do. Once we set about to go do it, it's just like any other problem that doesn't have a context. $20 and 23. Well, this will be 400 and 529. Okay, here's another interesting case where I don't think I'm really that interested, again, in the context of football, with the exact answer of the square root of 929. If you were to tell that to your average football fan, I think you would probably just get a dumb look. Like, you got a quarterback who made a pass in a game that was the square root of 929 yards. Well, if we were just getting this information from observations of the game, our measurements are approximations anyway. So we have to, kind of accept that we just have an approximate answer. 30.47 yards is a much better answer for this problem. Okay, you got a quarterback that made a pass in a game that was just over 30 yards. Okay, that answer is much easier to understand. Estimating annual revenue with FedEx, right? My guess is this data is probably coming from around the time of the Amazon boom, which I'm sure FedEx loved. You can go buy anything you want online. Somebody's got to ship it to you. FedEx will do it. They'd love to. Now notice on this one, it wants to use the information here for us to estimate their revenue in 2003 from data that we have on their revenue in 02 and 04. You'll see this from time to time with examples in my notes. There's the answer. Okay, I'm not that interested in, just an answer. Mathematics is the evidence that you show to support it. And here there's not a ton of work, but we have a little bit that we could show as to where those numbers came from. Well, here they are. 2003 is technically coming from 2002 plus 2004. Those were the 2 years in the problem we were given data on. Average those numbers, and you're going to get 2003. Take their revenue from 02, 20.6 billion, and then take their revenue from 04, 24.7 billion. Average those as well. There's our year, and that is going with this Y value, which is in billions of dollars of 22.65. Okay, not a lot of work, but it's important work, because that work shows the application of this midpoint formula and how we got that answer. All right, last topic of the lesson, translating points. Okay? Translating. The word I want you to associate that with is moving. Moving points. Okay? Moving points around on a graph. Okay? Now I've got 6 points. No context to them. There's no obvious relationship. It's not like the last problem where X was years and Y was, revenue. There's no obvious context as to how these numbers are related, just a random set of points. You'll see that very frequently we do this to an entire graph, where somehow we've got this, a lot of times a function, which we haven't talked about yet, but we'll get there. And we want to move the whole thing. We don't want to change the shape, but we just want to move the whole thing. That's where translations come in. Let's say in the last example that FedEx, went back to their accounting office and said, you know what, in all of our projections, we were actually, had an underestimate of $1 billion. Well, that was the Y variable, so we may need to move the whole graph up 1 unit, if we needed to add another $1 billion. Okay? So let's say we just want to take these points and we want to move them to the right 3 and up 2. Okay? In general terms, this is what needs to happen. Every point needs to go through this process. Okay? Every x coordinate needs 3 added to it. Every y coordinate needs 2 added to it. Okay? Now I'm not going to plot them. You can certainly do that if you would like. I think at this point we're probably good with just plotting points. I think that's a skill that most of you are very good at. I'm going to go through just 1 point at a time, like negative 1, 2. That's going to translate to the point 2, 4. 1, negative 4, that is going to become the point 4, negative 2. 2, 3, that's going to become 5, 5. The point 2, 4, that would become 5, 6. 4, negative 2, that would become the point 7, 0. And 5, 5, that would become the point 8, 7. Okay, and each one of those points have undergone that particular translation.